Here we go. Polynomial identities. Polynomial identities are those. We've already been working with them. And so the idea of today's lesson is to prove polynomial identities. So I'll get into that in just a second. So the goal for today, first of all, says to prove polynomial identities by using them to describe numerical relationships. All right. An identity is an equation that is satisfied by any numbers that replace the variables. So it's basically like a rule, right? If you have a generic rule for something, that's an identity, like y equals mx plus b, or the quadratic formula. Those would be identities. So a polynomial identity is a polynomial equation that is true for any of the values that are substituted in for the variables. And the reason why we were able to factor the way we did the last 2 days is because of those identities. Otherwise, it would have been a lot more challenging. Because it works for all cases, we could look at the type of polynomial that we had, and we said, oh, it's like that one, so we're just going to factor it like that, and it worked. So, unlike solving an equation, do not begin by assuming that an identity is true. You cannot perform the same operation to both sides and assume that the identity is maintained, or that the equality is maintained. So basically, you're going to prove it by just doing some generic algebra and checking to see if it equals the original thing that it is said to equal. So right here it says, oftentimes it's easier to work with the more complicated side of an equation. Look at each side to determine which one requires more steps. For example, it's often easier to work on the side that involves the square root or the cube of an algebraic expression. So verifying identities by transforming one side. That's what I was just mentioning. Simplify one side of an equation until the two sides are the same. If it ends up being that the two sides are the same, that means you've proved that it works and that they are the same. It's often easier to transform the more complicated expression into the form of the simpler side. Factor or multiply expressions as necessary. Simplify by combining like terms. For example, if we take a look right here, this polynomial identity is the identity for difference of cubes. Instead of a and b, though, it's using x and y, but it's the same thing. And so if we want to prove that those two things are equivalent, all you would have to do is on the right side, distribute and combine like terms. That's literally it. So if you take the x and you distribute it to the x squared, the xy, and the y squared, and then take the negative y and distribute it to the x squared, the xy, and the y squared. And I don't like the way they do the distributed property in this book, so I'm going to scratch out line 2. We don't need that. And we're just going to go through. We're going to multiply 6 things together, and then we'll combine some like terms. And if it ends up being that those two things are exactly the same once we do that work, then that means we've proved the identity. So what is x times x squared? X to the third power, yeah, x cubed. X times x squared is x cubed. So the first term here is x cubed. Then we're going to multiply x by xy. Well, we're multiplying an x times an x, so that would be x squared. And then there's a y there as well, so that would be x squared y. And then it's multiplying by x by y squared, which it shows right here is xy squared. Then we're going to take negative y and multiply it by x squared. Now, when you do this, write them in alphabetical order. That'll make things easier. So y times x squared would be x squared y. So alphabetical order. So you're going to have minus x squared y. And then negative y times xy would be negative xy squared, because there's two y's multiplying together, so y squared. And then negative y times y squared would be negative y cubed. So you could just finish the problem after this. It went ahead and matched up everything that was a like term together. So it took this x squared y and it matched it up with that x squared y. So it took this x squared y and it matched it up with that x squared y. So it's just taking the like terms and putting them next to each other, which is not a necessary step, but it can be helpful in case you're having a hard time visualizing what's going on. I want to make it clear that the pink ones and the blue ones are not like terms with each other because it matters where the squared is in those terms. This squared is with the x. That squared is with the y. So those are not like terms that are next to each other right here. Yes, they both have a squared term and a non-squared term, but the squared term must be with the same term in order to be like terms. So what happens to the x squared y and the minus x squared y? They cancel, yeah. If you have a positive x squared y and a negative x squared y, those cancel out. What happens if you have a positive xy squared and a negative xy squared? Those cancel as well, which means we're left with what? Well, in the middle, yes, but we still have a term at the beginning and the end that we didn't deal with, that we can't deal with, I should say. Yeah, x cubed minus y cubed. Is that equal to the original left side of the equation? Yeah. So that proves the identity. So it's just distributive property combined like terms. It proved that that is true. That's all you have to do. So because the expression on the right can be simplified to be the same as the expression on the left, this proves the polynomial identity. It just takes some algebra and distribution and like term combining, and we're good to go. Any questions on that before we look at the last couple examples on the next page? Very short lesson today, kind of like Tuesday. It's great. All right, example 2. Our buddy Pedro here. It says that Pedro claims that you can always create 3 lengths that form a right triangle by using the following method. Take 2 positive integers, x and y, where x is greater than y. Whatever x is has to be more than y. All right. 2 legs of a right triangle are defined as x squared minus y squared and 2xy. So here's a right triangle, x squared minus y squared, and there's 2xy right there. Those are the legs. The hypotenuse is defined as plus y squared, which is right here. Is Pedro correct? Explain your reasoning in the context of polynomial identities. So what do you know about the relationship between the side lengths in a right triangle? What do you know about the relationship between the lengths of the sides in a right triangle? Anybody remember? What's that? What's equal? Let's see if this rings any bells. Let's say this length is called A, this one's called B, and this one's called C. Close. Yeah, A squared plus B squared equals C squared, the Pythagorean theorem, right? Okay. So we could try to use the Pythagorean theorem to work through this. So it says to determine whether Pedro is correct, we can use information about right triangles, like the Pythagorean theorem, and expressions involving x and y to try to construct a polynomial identity. If x squared minus y squared and 2xy are the legs of the triangle and x squared plus y squared is the hypotenuse, then it should be true that a squared plus b squared equals c squared. Because a was x squared minus y squared, b was 2xy, and c was x squared plus y squared. So it should be true that that needs to be true if this is actually a right triangle. Because if it doesn't equal each other with a squared plus b squared equals c squared, then it can't be a right triangle. Everybody good so far? Okay. So then we set up the equation, and we have to evaluate both sides of this equation. So let's get that going. If we square x squared minus y squared, that means you essentially have to FOIL. And if you want to write in an in-between step, you're welcome to do that. But I'm just going to say first outer inner last. First times first is x squared times x squared. That's x to the 4th. Outer would be x squared times negative y squared, which would be minus x squared y squared. Inner would also be the same thing. So minus x squared y squared minus x squared y squared. That would be 2 that have a minus x squared y squared, which would be minus 2 x squared y squared. And then negative y squared times negative y squared is positive y to the fourth. So those three terms there is this squared out. Here, 2xy squared, just apply the square to everything. 2 squared is 4, x squared, y squared, right there. Now over here, it's going to be just like this one. The only difference is instead of in the middle being a minus 2, it'll be a plus 2 instead. So there's that. All right. And then if you combine like terms, I should mention that as well. The x squared, y squared terms here and here, negative 2 plus 4 equals what? X squared, y squared, x squared, y squared. Those are like terms. Negative 2 plus 4 is what? 2, which x to the fourth plus 2x squared y squared plus y to the fourth equals x to the fourth plus 2x squared y squared plus y to the fourth. So it's the same on both sides. So that's good. Because the identity is true, this proves that Pedro is correct. His process for creating the sides of a right triangle will always work. All right, that's cool. So let's go ahead and take a look at this last example, and then we'll call it a day. So we got x to the fourth minus y to the fourth. This is an identity that we have not seen before. So in terms of proving it, we'll have a little bit of work to do because we've never done this before. So let's go ahead and start by using FOIL with these first two terms here, which would be x squared. Here's the original equation. So x squared, if you FOIL that out, I'm just going to go ahead and write this. It'll be x squared plus xy minus xy minus y squared. And then we'll have x squared plus y squared right there. And these two terms in the middle, positive xy minus xy, those are going to cancel, leaving us with x squared minus y squared. So you've got x squared minus y squared times x squared plus y squared. And then we FOIL those out. First times first, x squared times x squared, x to the fourth. Outer, x squared times y squared is going to be x squared y squared. Inner, negative y squared times x squared, right in alphabetical order, will be minus x squared y squared. And then y squared times negative y squared equals negative y to the fourth. The two terms in the middle, those are like terms. One's positive, one's negative of the same value. So those are going to cancel as well, leaving us with x to the fourth minus y to the fourth. And it says to write in the missing explanations. So from this step to this step, what did we do? From here to here, what did we do? FOIL, yeah. And then from here to here, we FOILed again. And then the two terms in the middle, what do we do with those? Canceled. And so when you cancel terms, what are you doing? You can only cancel terms if they are what? If they're the same. So that would be combining like terms. Nice. So combine like terms. All right. That's it. That's the entire lesson. So we're out of here at 1:42 today. We've got 36 minutes. Nice. Hopefully you won't need to come for TAT to finish up lesson 5 too, because you get a lot of time to work.